So when we move down the group, the size of the atom will keep on increasing. I hope it is clear. Yes, because more and more shells is being added on. So what is metallic radius? It is half of the internuclear distance between two metallic ions in a metallic crystal. The value of ionization enthalpy increases with nuclear charge. So van der Waals radius will be always higher than covalent radius because it is between two atoms of two different molecules, right? Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So in last session, we discussed on Dobereinius triads, Newland's law of octaves, Mendeleev's periodic table, and finally, we discussed about the modern periodic table in detail, right? Then electronic configuration of elements and the periodic table. Yes, the electronic configuration in the periods as well as the groups we discussed, right? Then we discussed on the 4 blocks, right? S block elements, P block elements, D block elements and F block elements. Yes, so in today's session, we are going to discuss on nomenclature of elements with atomic number more than 100. Then metals, non-metals and metalloids, about noble gases and trends in physical properties. Yes, we are discussing about atomic radius, ionic radius and ionization enthalpy in this session. Okay, yes, so to begin with, the nomenclature of elements with atomic number more than 100. Yes, so nomenclature, we are going to name the elements which are having an atomic number more than 100. So why is it actually a new method being discovered for naming the elements which is having atomic number more than 100? So what happened is, after the scientists started discovering elements which is having atomic number more than 100, there happened a fight between the scientists. Like many elements were being discovered and many scientists wanted to take credit for the same element, the discovery of the same element. So to avoid a confusion happening between who named the element or which scientist named the element, a system was adopted by IUPAC which helped to nomenclature, that is, name the elements which are having atomic number more than 100. So, for naming elements with atomic number greater than 100, IUPAC has made some recommendations. A systematic nomenclature can be derived directly from the atomic number of the elements using the numerical roots for 0 and numbers from 1 to 9. So, what did IUPAC do? Yes, so for the numbers from 0 to 9, they gave a particular name. Okay, so using that and the abbreviations that you can see that is given there. So using these names, the atomic number, the elements having atomic number more than 100 can be named. So let's try to understand this. Let us take the example of the element having atomic number 101. 101. So according to IUPAC, yes, you can see the digit having, if the number is 0, the name is nil. For 1, it is un, 2, it is bi, 3, it is tri, 4 is quad, 5 is pent, 6 is hex, 7 is sept, 8 is oct, and 9 is n. Okay, so how exactly do you have to name these elements? Let's see. So let's take the example of 101. Okay, so from the table you can see, corresponding to 1, what is the name? It is un, right? So you have to write that first, un. Then comes 0. Yes, for 0 the name is nil. So un, then without any gap you have to write nil. Then again comes 1, that is again un. Un, nil, un. And once you are done with this, you have to add an IUM. Okay? Yes. After you name the element based on the table, finally you have to add an IM to it, that is IUM. So what is the name for the element having atomic number 101? It is un, nil, unnium. Right. Let's take the example of 102. Okay. So for 1 it is un. Yes. For nil it is 0. Yes. 0 it is nil. The name is nil. And 2 it is bi. Yes. Un, nil, bi is written. I said you have to add em. Right. So IUM. So it is un, nil, bi, em. So other examples are given here. For 103 it is un, nil, tri, em. Right. For 1 it is un, 0 it is nil, 3 it is, you can see 3 is tri, right? So unnil triem, em has to be added in the end. For 104 it is unnil quadium. 105 it is unnil pentium. 106 it is unnil hexium. 107 it is unnil septium. So let's take another random example. 117. Right. How would you name it? Yes, for 1 it is. So for 1 the corresponding name is un. Then again 1 un. And for 7 it is sept, right? So I write sept and then what do I have to do? I have to add IUM there. So the atomic number 107, the element having atomic number 117 is having a name unseptium. So this is how you, I hope you understood. So this is how you name the elements having atomic number more than 100. So using this table, any element having atomic number more than 100 can be named. Yes, I hope it is clear. Yes. So moving on to the next part, we are going to discuss about metals, non-metals and metalloids. The basic properties of metals, non-metals and metalloids we are going to discuss now. So you have already studied about metals, non-metals and metalloids. You already have an idea about it. So extra on to that, we are going to study how the metallic character and non-metallic character will change across a period or down the group. We are going to see all that. So what you can see from the periodic table is that, see, the dark blue region that you can see, all of that are metals. So you can say around 78%, yes, of the periodic table of the known elements or as you can see in the periodic table, this much part is metals, right? And this black part you can see, this area, that consists of the metalloids. Yes, metalloids are elements having properties which is both of that of metals and non-metals, or you can say in between that of metals and non-metals, right? And this light blue region that you can see, that belongs to the non-metals. So the elements present in that part is non-metals. So you can see from the picture itself you can understand, right? This much part is metal. So it consists of 78% of all known elements. Right. So discussing on the properties of metals, we know that they are solids at room temperature, right? And then they have high melting and boiling point, and they are good conductors of heat and electricity. They are malleable and ductile. So what is malleable and ductile? Malleable means malleability. It means that the metals can be made into thin sheets, right? Ductile means the metals can be made into thin wires. Right. So metals are malleable and ductile, and the metallic character increases down the group and metallic character decreases along the period. Now what is this? This is what I was talking about, the trends, how the metallic character will change across the period and down the group. So that we are going to see. So what exactly is metallic character then? So metallic character means it is the tendency of an element to give away its electrons. So, or you can say that how easily a metal can lose an electron. Okay. So, if the metal can easily lose an electron, we can say that the metallic character is high. So, what is given here? The metallic character increases down the group. So, when we move, let's consider the first group. When we move from the top to bottom, that is down the group if we move, yes, the metallic character increases. That is what is given here. So, what exactly is that mean? Okay, so metallic character increases. So as I said, metallic character means how easily the element can lose an electron, right? So let us consider the example. There is a nucleus, okay, and there are shells present, right? So for lithium, we know that it is 1s. Yes, what is the electronic configuration of lithium? It is 1s2 and 2s1, right? So in the first shell, there are 2 electrons. And in the second shell, there is 1 electron, right? So that is lithium. Now moving on to sodium, we are moving down the group. Yes, we know that the electronic configuration is 1s2. Yes, for sodium, it is 1s2, 2s2, 2p6 and 3s1, right? So one more shell is added, right? As a nucleus and 1, 2, okay? So, in the first shell, yes, in the first shell, there are 2 electrons, and in the second shell, there are a total of 8 electrons, right? 6, 7, 8. And in the last shell, that is the third shell, there is 1 electron. So what you can understand from this, when we move down the group, that is from lithium to sodium to potassium, the number of shells is increasing. Yes, in the case of lithium, there is 1s and 2s. And in the case of sodium, it is 3s now. Yes, one more shell is being added, right? So when we move down the group, the size of the atom will keep on increasing. I hope it is clear. Yes, because more and more shells is being added on. So you can see from here to there itself, you can see the size of the atom has increased. So when we move down the group, the size of atom increases, right? So as said, metallic character means easily the electrons should be able to escape out, right? So that means when we are moving down the group, as the size of the atom increases, the attraction between the nucleus and the outermost electron will become less and less, right? So easily the electron can escape from the outermost shell, right? So what is metallic character? It is a tendency to lose electron. Yes, how much easy it is, that much metallic character will increase. So what you can understand, when we move down the group, as the size increases, the attraction between the nucleus and the electron will keep on decreasing. So easily the electrons can be removed from the outermost shell, right? So hence the metallic character increases down the group, right? Now metallic character decreases along the period. Yes, so let's consider this period, that is sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. So when we are moving along the period, what is happening? Is the shell number increasing? No, right? What is the electronic configuration of sodium? It is, yes, 1s2, 2s2, 2p6, 3s1. For magnesium, what it is? 1s2, 2s2, 2p6, 3s2, right? Yes, so it is, the electron is added on to the same shell, right? Yes, so when we move along the group, the electrons are being added on to the same shell. So what happens? More and more electrons are present in a particular shell. So the attraction between the nucleus and the electrons keep on increasing. Now the electrons and the nucleus will be having very high attraction between each other. So will the electron be easily be able to remove from the shell? No, right? We can't easily remove it. So the tendency of the electron to get lost from the shell will decrease. So that means the metallic character decreases along the period. So I hope it is understood. Now moving on to non-metals. So non-metals are solids or gases at low temperature. They have low melting and boiling point, and they are poor conductors of heat and electricity. Right. Now what about non-metallic character? Non-metallic character means the ability to accept one electron, right? So non-metallic character increases along the period and non-metallic character decreases down the group. Yes, so as we have discussed about metallic character, when we move down the group, what happens? Yes, the atomic size keep on increasing. More and more shells will be added, right? So what is non-metallic character? It is the ability to accept one more electron, right? So what happens when the size keeps on increasing? It is difficult to add one more electron, but the atom will be able to lose an electron easily, right? It is difficult to add an electron onto it. So what happens? The non-metallic character decreases down the group, right? Now non-metallic character increases along the period. If you are moving along the period, yes, in the same shell, more number of electrons is being accommodated. So yes, the atom can accommodate more electrons to it. Right. So the non-metallic character increases along the period. So more and more attraction will be there between the nucleus and electrons. So that is about non-metals. Now the elements showing characters of both metals and non-metals are called as metalloids. Hence they are also called as semi-metals. Okay. Yes. So the same diagram that we saw in the beginning. Yes, this much part is metal. See, only these many elements are having the semi-metal properties, that is, they are the metalloids. Yes, and this part is the non-metals. So I hope you are clear with metals, non-metals and metalloids and the trends in metallic character and non-metallic character. Yes, so moving on to the next part, that is noble gases. Now what about noble gases? They belong to the group 18. So yes, the last group that you can see, right, starting from helium. Yes, this whole group is the noble gases. Now, what is the speciality of noble gases? They already have attained octet. That means they have 8 electrons in its outermost shell. Yes, so what do we know about octet rule? Once the shell is having, that is, it satisfies its octet, yes, they are stable. They need not go for reaction, right? So why does actually the chemical reactions take place? Because either the atom requires electron or it wants to lose electron, right? But once the octet is completed, right, the element need not undergo reaction. So hence they are also called as inert gases because they do not generally undergo reactions, right? So each period ends with noble gas element. Yes, we saw in the periodic table. They are of gaseous nature. So noble gases, as the name only suggests, they are gases, and having filled orbitals, they have very little tendency to take part in reaction. As I said, their octet is completed, so they need not take part in the reaction. So this is about noble gases. Now moving on to the next topic, that is trends in physical properties. So how the physical properties will change along the period or down the group, we are going to study in this section. What is the trends in these physical properties? So first we are beginning with atomic radius. Right. So what is atomic radius? From the name itself, you can understand that it is the radius of the atom. Right. So let's see the definition. It's the distance from the center of the nucleus to the outermost shell containing electrons. Right. So if I am considering this particular atom, right, from the center of the nucleus to the outermost shell containing electron, what is the distance between them? Yes, from the center of the nucleus to the shell containing the outermost electron, right? So the distance is called as the atomic radius. So there are different types of atomic radius based on how these atoms are being combined with each other. So let's see, the first one is covalent radius. So as you can see, it is covalent radius, means the atoms will be covalently bonded, right? So it is half of the internuclear distance between two covalently bonded atoms, and it is used to express the atomic radius of non-metals. So what is covalent radius? Half of the internuclear distance, that is from the one nucleus to other nucleus. Yes, two atoms are covalently bonded. The distance between the nuclei of each of these atoms is the covalent radius. So as you can see here, see, two atoms are covalently bonded from the center of the nucleus of one atom to the center of the nucleus of another atom. The distance between them, the half of it, right? This is the distance between them. And if you take the half of this, that will give you the covalent radius. It is half of the internuclear distance, right? So from this nucleus to this nucleus, that is the internuclear distance. Half of it will give you covalent radius. So they must be covalently bonded, right? So that is about covalent radius. Now van der Waals radius, what it is? It is defined as half of the internuclear distance between two non-bonded atoms of separate molecules in the solid states. So what is this? Yes, as you can see, half of the internuclear distance between two non-bonded atoms of separate molecules. Okay, it is the distance between half of the internuclear distance between two atoms of different molecules, right? Of different molecules. As you can see here, this particular one is one molecule and this is another molecule. And it is half of the internuclear distance between two non-bonded atoms of two different molecules. So let's consider this one and this one. This is atom of one molecule. This is atom of another molecule. The internuclear distance between them is this part, right? And the half of it will give you van der Waals radius. So I hope you understood the difference, right? It is the it belongs to two different molecules, the atoms of two different molecules. Clear? So that is, yes, as you can see here, yes, it is non-bonded, right? They are not bonded with each other because they are part of two different molecules. Half of the internuclear distance between them will give you van der Waals radius. Now moving on to the third one, that is metallic radius. So what is metallic radius? It is half of the internuclear distance between two metallic ions in a metallic crystal. So metallic radials. So from the name itself, it is the distance or the internuclear distance, half of the internuclear distance between two metallic atoms, right? Yes. So metallic radius, two atoms of metal, and the half of the, yes, half of it will give you the metallic radius. So I hope it is clear. So what exactly is the difference between covalent radius and ionic radius? As you can see, this one and this one, they are covalently bonded, right? And here also this and this one are covalently bonded. So the half of this will give you the covalent radius. Now the distance between this two, this atom and this atom, the half of it will give you van der Waals radius. Clear? So from this itself you can see which one will be the higher value. Will it be covalent radius or van der Waals radius? As you can see, this is the covalent radius, right? And this is van der Waals radius. So van der Waals radius will be always higher than covalent radius because it is between two atoms of two different molecules, right? So of course the van der Waals radius will be more than the covalent radius. So I hope it is clear. Now moving on to how this atomic radius will change along the period or down the group, we are going to see. So along the period, the atomic radii of elements decreases. Yes, this is because in a period, the electrons are added to the same valence shell. Thus, the number of shells remains same, but the effective nuclear charge increases. So, the atomic radius decreases. Clear? So, what happens? Along the period, if you are moving from this direction, yes, the atomic radius keeps on decreasing. So, why this is happening? Yes, what is written here? This is because in a period, electrons are added to the same valence shell. We discussed about it before also. Along a period, the electrons are being added onto the same shell. Right, the shell number is not increasing. That happens down the group. So, along the period, on the same shell, the electrons are being added. So, the nucleus which is present in the center, it starts attracting the electrons more and more. The effective nuclear charge increases, right? As the nuclear charge increases, that means the electrons will be pulled more and more towards the nucleus. So, pulling the electron more towards the nucleus, from that what you can understand? Yes, the size will become small and small, right? Hence, the size will decrease. Yes, more number of electrons are added onto the same shell. So, more effective nuclear charge, more and more pull will be there towards the nucleus. So, what happens? The size decreases. So, as you can see from the diagram, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Yes, if we move along the group, the atomic radius is decreasing. Yes, clear? Now, moving on to how the atomic radius changes down the group. Atomic radius of elements increase as we move down the group. Why? This is because the increase in number of shells and shielding effect. In atoms with higher atomic number, the inner electrons partially shield the attractive force of the nucleus. So, the outer electrons do not experience the full attraction of the nucleus, and this is known as shielding effect or screening effect. So, what did you understand from this? Yes, atomic radius of elements increases as we move down the group. So, we know that as we move down the group, yes, more and more shells are being added onto it. So, that of course means the size of the nucleus will keep on increasing, right? So, as more and more shells are being added, as you can see, when more and more shells are being added, yes, the attraction between the nucleus, that the positively charged nucleus, and the electrons will keep on decreasing, right? So, what happens? The pull, attractive force with which the nucleus can pull the electron will keep on decreasing. So, what happens? The size will not decrease, right? It will keep on increasing because more and more shells are being added. So, you can see from the diagram, yes, lithium, sodium, potassium, rubidium, cesium. Yes, down the group, the size of atomic radii is increasing. Yes, so I hope it is clear. In the case of halogens also, fluorine, chlorine, bromine, iodine. Yes, as we move down the group, the atomic radii is increasing. So, this is about the trend in atomic radii. Now, moving on to the next topic, that is ionic radius. So, we discussed about atomic radius, in which we discussed covalent, metallic and van der Waals radius, right? Now, we are moving on to ionic radius. Now, in general, ionic radii of element exhibit the same trend as that of atomic radii. So, how atomic radii is varying along the period and down the group, the same trend ionic radii will also show. Now, what exactly is ionic radii? It is the distance between the cation and anion in an ionic crystal. So, in an ionic crystal, there will be ions, right? So, as the name suggests, it is ionic radius. So, it is the distance between the cation and anion, that is positively charged ion and the negatively charged ion, right? So, what is cation? The removal of an electron from an atom forms cation. Yes, let's consider sodium. Okay, Yes, if an electron is removed from sodium, what happens? Sodium becomes sodium plus ion, right? So this positively charged ion is called as cation, right? Yes. Now, moving on to anion. Gain of one electron leads to the formation of anion. So when an atom gains an electron, let's take the example of chlorine. So what happens? When chlorine gains an electron, what happens? It becomes Cl minus ion. That is a negatively charged ion which is called as anion. Right. So this part is clear. Now, coming back to cation. Cation is always smaller than the parent atom. Okay, this is important. Cation is always smaller than the parent atom. Why? From the atom, when the atom lost one electron, it became cation. Right. So this is because a cation has fewer electrons, but its nuclear charge remains the same as that of the parent atom. So what happens is, when the atom loses one electron, right, it becomes a positively charged ion. So one electron is less there, but the nuclear charge, yes, the nucleus or the protons present in the nucleus, the pull with which they are pulling the attractive force with which they are pulling the electrons will be the same. Right, one electron is being lost means the nuclear charge is also remaining the same, means more and more pull will be there. So what happens? The size will become reduced. Yes, lesser number of electrons means more pull, right? Because the nuclear charge will remain just the same. Right. Now about anion, gain of one electron leads to the formation of anion, and anion is always larger than parent atom, because anion means one electron is being added on to it, right? The atom is gaining one electron. So what happens? One more electron is being added, right? So this is because the addition of one more electron would result in an increased electronic repulsion. So already few electrons will be there. Right, one more electron is being accepted. So we know that all these electrons are negatively charged, so they will start repelling each other, and then hence a decrease in effective nuclear charge will take place. So the attraction between the nucleus and electrons, yes, the effective nuclear charge will decrease. Hence, what happens? Yes, the size of the atom increases when it is forming an anion. Clear? So that is about cation and anion. So as you can see here, yes, the size of the cation is smaller than the size of the anion, right? Because as we discussed, the size of the cation will be smaller than the parent atom, right? And the size of the anion will be larger than the parent atom. Yes, so this is the radius that you can see here. Yes, so I hope it is clear, ionic radius. Now moving on to isoelectronic species. Okay, even this is a very important topic. What is isoelectronic species? From the name itself you can say same number of electrons, right? So they are atoms or ions which contains same number of electrons. So let us take the examples which I have given here. O2 minus, F minus, Na plus and Mg2 plus. So all these ions are having the same number of electrons. So let's consider the first one, O2 minus. Yes, so the number of electrons in oxygen atom is 8, right? Yes, plus 2 electrons. That is 2 minus means more 2 electrons are being present there in the oxygen atom. So it became an oxygen O2 minus ion, right? Yes, so this 2 minus will be an addition of 2 electrons. So that gives plus 2 will give a total of 10 electrons. So that will give a total of 10 electrons, right? Now let's move on to the next one, that is F minus. Okay, so we know that the atomic number of fluorine is 9, right? Yes, so the number of electrons will also be equal to 9. Yes, and there is a negative sign here. That means one more electron is being added. So that means a total of again 10 electrons will be present. Now let's take Na plus. What is the atomic number of sodium? It is 11, right? So in this case, Na plus ion, it is existing as Na plus ion. That means one electron is being lost from the atom, right? And hence it formed a cation. So that means one electron is less. Again, 10 electrons, right? Now last one is Mg2 plus. Now what about Mg2 plus? Atomic number of magnesium is 12. That means number of electrons is 12 plus 2 is given here. Yes, the charge is plus 2. That means 2 electrons are lost from the atom. So, a total of again 10 electrons will be present in this. So, as you can see, in all these ions, yes, all these ions, the total number of electrons is the same. That is 10 electrons. So, such species are called as isoelectronic species. Yes, I hope it is clear. Now, moving on to the next part, that is ionization enthalpy. Yes, we are going to study what is ionization enthalpy and the trends in ionization enthalpy in along the period and down the group. Same as that we studied atomic radii. Clear? Now, what is ionization enthalpy? It is the energy required to remove an electron from an isolated gaseous atom in its ground state. So, it is the energy required to remove an electron from its outermost shell. So, let's take this example of magnesium. We know that the atomic number of magnesium is 12, right? So, that means there are, yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, a total of 12 electrons are present. Yes. So, in here, if I want to remove this electron from this particular shell, yes, if I want to remove this electron, a particular amount of energy is supposed to be given there, right? The electron simply will not just get escaped from the shell, right? An energy is required to be given to the atom so that the electron is being removed from the shell, right? So that energy which is required to remove an electron from, yes, isolated gaseous atom in its ground state. So that energy which is required to remove an electron is called as ionization enthalpy. So once that electron is removed, what happens? It becomes an ion, right? So that is ionization enthalpy. So ionization enthalpy increases along the period. Okay, so along the period, because nuclear charge increases and the size decreases. So why does it increase? Ionization enthalpy, why does it increase along the period? So what do we know? Once we go along the period, so what did we study? Yes, along the period, the size of the atom keeps on decreasing. We already studied this, right? Yes. Now, how does it relate with the ionization enthalpy? Okay, let's see. In this case, an electron is present on the outermost shell and energy is required to remove it. Yes, remove the electron from the shell. Yes, an energy is given here. Now, as the size is decreasing, yes, we know that why the size is decreasing, because there is an attraction, more and more attraction between the nucleus and the electron. So, if they are highly attracted with each other, will it be easy to remove the electron from the outermost shell? No, right? Here it will be easy because the attraction is quite less. But when we are moving along the period, more and more electrons are being added and the nuclear charge increases, right? We already know that. So, when the nuclear charge is increasing, that means the attraction between the nucleus and the electron is more. So, will it be easy to remove the electron now? No, right? So, as we move along the period, the ionization enthalpy increases. That means more energy is required now to remove the electron. Hence, ionization enthalpy increases. Clear? Now, ionization enthalpy decreases down the group because the nuclear charge decreases. Yes, we know that as we move down the group, what happens? The size increases. Yes, so now the attraction between the nucleus and the electrons keeps on decreasing, right? Hence, the nuclear charge also decreases. Yes, so what happens? It will be easily removed. The electron can be easily removed from the outermost shell. Yes, because the size is increasing and the attraction is becoming less. Yes, so if the electron can be easily removed, that means only a very little amount of ionization enthalpy is to be given there, right? So, as we move down the group, the ionization enthalpy decreases. Now, energy is always required to remove an electron from an atom or ion, right? So, as I said in the beginning, electrons will just not escape by itself, right? An energy is required to remove an electron, right? Hence, the ionization enthalpy, delta IH, is always a positive value. Now, the second ionization enthalpy is always higher than the first ionization enthalpy. This is because it is more difficult to remove an electron from a positively charged ion than a neutral atom. Similarly, third ionization enthalpy is higher than the second ionization enthalpy, and so on. So, what is this? Okay, so let's take this example itself. So, I want to remove one electron from the magnesium atom. Yes, so the first ionization enthalpy is the energy required to remove the first electron from the magnesium atom. Now it became a magnesium ion. Yes, a positively charged magnesium ion, Mg+, because one electron is being removed. Now I want to remove the next electron. Now this is gone. Yes, the next electron, the second electron is also to be removed. So if I remove this electron, right, so now I am removing the electron from Mg+ ion, not Mg atom, right? One electron is already gone. From this Mg+ ion, I am trying to remove the second electron. So Mg+ ion means, yes, one electron is being lost. That means one electron is less. So what happens? The nuclear charge increases. Now the electrons is having more attraction with the nucleus. So what can you say? Now to remove the second electron, more energy is required, not the same as the first ionization enthalpy. Now to remove the second electron, that is ionization enthalpy 2, more amount of energy is required, right? So ionization enthalpy, that is second ionization enthalpy, will be greater than first ionization enthalpy. Okay, now it becomes Mg2+ ion. Right, 2 electrons are removed. Now, if I want to remove one more electron, yes, that is 2 electrons are already lost. So, the nuclear charge has more increased. Now, if I want to remove one more electron, that is more amount of energy I have to give. That is ionization enthalpy to remove the third one. That is third ionization enthalpy will be greater than the second ionization enthalpy, and that will be greater than the first ionization enthalpy. So what you can understand, the first ionization enthalpy will be the least. So as we keep on removing more electrons, what happens? More amount of energy is required. Right, because the attraction or the nuclear charge keeps on increasing. So I hope it is clear. Now, which are the factors on which ionization enthalpy depends? So the first one is atomic size. So greater the atomic size, smaller will be the ionization enthalpy. So we already discussed this. When the atomic size, yes, more and more shells are introduced, that means size is being increased. Like more size means easily an electron can be removed from here. Yes, because the attraction is less now between the nucleus and electron. So easily it can be removed. That means a very less amount of ionization enthalpy is required. So what does that mean? Smaller will be the ionization enthalpy when the size keeps on increasing. Now second factor is nuclear charge. The value of ionization enthalpy increases with nuclear charge. That means, yes, more nuclear charge means what? Yes, the nucleus and electrons are having a very good attraction with each other. Now, if they are having a good attraction with each other, and if I want to remove an electron from it now, more amount of energy is required, right? Yes, hence the value of ionization enthalpy increases as the nuclear charge increases. Now, the third one is shielding effect. Yes, as the shielding effect increases, the electrons can be easily removed, and so the ionization enthalpy decreases. So what is shielding effect? We have already studied this, right? Yes. Let's take this particular atom in which 2 electrons are here. In the second shell, there are 8 electrons. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And in the last shell, 1 electron is here. Now, because of the electrons present in the penultimate shell, yes, they cause a shielding, yes, with the attraction, shielding for the attraction of the nucleus towards the last electron. So, this is called a shielding effect. These electrons will shield the attractive force of the nucleus towards the last electron. So, it will be less. The attraction will become less. So, if the shielding power of the penultimate shell is more, that means if the shielding power is increasing, that means they are very well shielding the nucleus from the outermost shell. Yes, so the electron will be loosely bounded there. So, easily we can remove it. Right. So, I hope it is clear. So, hence, as the shielding effect increases, what happens? Yes, easily the electron can be removed. So, that means only very less ionization enthalpy is required. The last one is presence of half-filled or completely filled orbitals increases the ionization enthalpy. So, we have already studied that for half-filled and completely filled shells, the stability will be more. When the atom is more stable, that means more ionization enthalpy is required. So, I hope ionization enthalpy are the factors affecting and the trends of the ionization enthalpy across the period and down the group is clear for you. In the next class, we will be discussing on electron gain enthalpy, electronegativity, periodic trends in chemical properties. So in this class, we studied about the periodic trends with physical properties, right? And then anomalous properties of second period elements and periodic trends and chemical reactivity, wherein we will end this chapter. Yes, so I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.